and it should be ready anytime. I would go.
All right. Well,
Well,
thanks to everyone for coming to the outreach portion of Roger That. We're super excited that you could join us. Just to give you a brief overview of what this part of Roger That is all about. Roger That is the public symposium on space exploration with the collaboration between Grand Valley State University, along with our partners at the Grand Rapids Public Museum. And it's a two-day celebration of the life of Roger B. Chaffee, to honor the life of Roger B. Chaffee. It's January 27th is when the Apollo 1 fire took place. And I think February 15th is his birthday. So this was kind of the right time to celebrate him. It's just the wrong time for Michigan that this weather-wise. But this year we have been able to go virtual. So we're very excited to bring this to you. And we still kept the Design That part of our challenge. And this is part of a very big, important part of Roger That, where we do outreach to schools in the area. And we have with us the Design That entries from the 4th through 6th graders from Grand Rapids Montessori. And usually these would be out and you could walk around and talk to the students. This time we have been forced to go virtual. So it will be Karen and myself doing the honors. We also have the team from the School of Engineering called the Moon Miners, who will be presenting their NASA Micro-G Next Challenge entry, one of only 20 universities. They are in the good company with the likes of Purdue and Berkeley. So we're very, very excited for that. This is I think the fourth or fifth time that GVSU's teams have qualified. And so we're very excited to bring you that. So with that, I'm going to start the presentation. So, oops, there we go.
Okay, so as part of the outreach, we had money set aside for catering, and when we were forced to go virtual, we decided to use that to create STEM kits to send out to the kids. So the kits included experiments for reflection, refraction, and diffraction, and they were packaged with instructions that we wrote. Then we compiled them into these nice shoe boxes and delivered them to the schools, and they dispersed them to the children. And I hope that they have had fun with them.
So I'd like to talk a little bit about the Design That Challenge. It was intended for 4th through 8th graders, right in that middle school, late elementary school area when students are really excited about science, and we wanted to tap into that. And we sort of made the design challenge very open-ended. We said you can solve any space-related problem, humans, communities, robots in space. And this year we added, due to the virtual nature of our Roger That, we added simulations in space. So you could simulate something in space. And we also kept it very wide open as to the kinds of things they could do. They could write a story, perform a play, they could design clothing, a building, or devices for space travel. They could design robots. So we had some very interesting entries, as you can see, in the past few years. And this year, I think we come to you with some fantastic entries too. So part of the project includes the children provide us with the project reflection. The reflection includes a creative title, why they chose the topic, what they found most interesting about the topic, something that they learned, something that they were surprised by, what they would do differently. And then also, because we believe in appropriate sourcing of everything, a detailed bibliography. So now we're going to talk a little bit about these projects that were part of the Design That Challenge. Most of our entries came from, well, all of our entries came from the Montessori school, from 3 teachers, and these are their projects.
And I would just like to say before I get started, one of the other questions we asked about in the reflection is what was most challenging? And to a T, all of them answered working remotely on the project. So we really appreciate the hard work that all of these students did. And they did some really amazing projects, both in teams and singly. So this project is called Mining in Space, and it was done by 2 team members, and they took turns speaking on a video. So most of the teams did present videos to us, and we will be compiling those into one source, and they will be posted on our website next week, hopefully, or maybe the week after that. But this team designed 2 things for mining in space. So one person designed the space suit, and they called it the Zeus space suit. And they had electrically heated top with gloves. And they obviously did a lot of research and figured out what the main problems were. So heating in space is a big topic. And then they had weighted pants with heavy boots. So you can see that on that picture as well. The other member of the team designed a probe for how to get the materials out of the planet. And so that probe was, they said the mining tool was made of synthetic diamond, and they had storage bays. It was like a car-like probe, and it had held 16 gallons of fuel and storage bays for the mine materials. And they were surprised to learn that different materials are needed for space. Rather than leather and steel, for example, different materials were needed for space.
All right, so I'm going to tell you about the project by Space Cats. And these are 3 team members, and they designed a cosmic moon base, and they took into consideration what kind of food they would serve, how they would create that, how they would get that food, how they would provide water, how to make artificial gravity, and how to create electricity on the moon. And they had a little diagram of what their moon base would look like. So it was very important for them that they have a plant-based diet in space. And so they were going to grow lots of peas and tomatoes and carrots, and also veggie burgers for people who preferred meat. And then they were going to use incandescent light bulb system to grow their plants under sunlight conditions to simulate sunlight. They'd use a filtration system using activated carbon to purify urine from water. And then finally, they were looking at things like artificial gravity. So they considered using a centripetal force with a rotating space station that would create that artificial gravity, and solar panels for electricity. They also thought about entertainment and how to keep people entertained on the moon. So they had an area for ping pong, air hockey, and more like that. So this was the Cosmic Moon Base.
And another team did a project only on artificial gravity, and they also made use of centripetal force. So they were clearly doing a lot of the same research. They designed a spaceship. This top picture is the space. Oh no, that's not the picture of the spaceship. They designed a spaceship that was called Airfoil 3A. That was very specific, and they said it had carefully designed curved surfaces. That's what they understood an airfoil to be. The other member of the team designed gravity boots, and these pictures are of the gravity boots. And they had obviously learned that centripetal force was a way to create gravity. And so they had the idea to have spinning magnets inside a glass ball, and they called their device Rational Rotation Ankle Disc. And so this is a picture both of the glass ball with the magnets inside it, and then the lower picture is a picture of the person using the artificial gravity boots.
And then now we have Team Allure, and the name of their project is The Reason Why It's Disappearing. And so they made a little movie about sending robot dogs to Saturn to collect data and take photos and solve the mystery of why Saturn's rings are fading. So they did a lot of research into the topic of Saturn rings and how scientists believe that they're disappearing. And then the solution to that problem was to take photographs and send them back to NASA. But I think they got a little distracted by the robot dogs, because they found that, something that surprised them was that there were robot space dogs. And so that became the prime focus of their project. And they have a film that they've made along with this that will be made available for your viewing pleasure after this conference is done.
And then the team named the Signs Girls wrote an illustrated story called Sarah Mazepin Goes to Space. And this is a picture of the illustration they submitted, which I thought was really beautiful. The story is the theme of a young child who learns about space when she's 9 years old, which is probably close to the age these students were when they wrote the story, are now. And Sarah did a lot of research and learned that it can take years to build this project, and that space is not supportive of basic human needs for oxygen, water, food, and air, and rest. And also there was a piece of the story that said Sarah was really nervous about her project presentation, and then it went well, and that really encouraged her to become a science fiction writer, which she did throughout her adult life. And so as an adult, Sarah traveled to space, but her rocket crashed on an unknown planet where she met an astronaut, had kids, and then she herself built the device to communicate back to Earth and got them rescued. And she continued writing science fiction stories for the rest of her life. So that was a really interesting project.
And so next we have a team called All Systems Go, and this was a 4-member team who decided to tackle the complicated task of building a spacesuit for kids. They'd seen a lot of spacesuits for adults, but there was really nothing available for kids. The current suits were too big, and the team was very interested in having kids go to space. So they did a lot of research on the kinds of life support systems that they would need for supporting a life within the spacesuit. And one of the things that surprised them, well, there were a couple of things that surprised them. One was just how heavy the current life support systems were. And so it might be a problem for kids. So they're trying to deal with it. They have a very nice video that accompanies this project about what kind of backpack would go with this and what they would put in that backpack to support life. And another thing that surprised them, that there was one company that made all the spacesuits for NASA, which is something that surprised me too. I had no idea about this. So this was All Systems Go.
And another team did a project on the trash removal. They learned that there was lots of trash in space, and so they wanted to do something about that. So they designed a robot to clean up the trash in space, and they also wrote a movie script about 2 kids, Ivy and Violet, who make a trash robot. And there was lots of glitter involved in the trash robot. And something that surprised them is that there's a lot of space junk, broken up satellites and space shuttles, and something can reach speeds of 18,000 miles per hour.
And then we had the team Super Cool 2, who did their project around building future communities on Jupiter. And so their big idea was to see if humans can live and thrive on Jupiter. And so one of the ideas they had, which you can see in this picture over here, is to build a dome around one of the spots of Jupiter so that they can create an artificial atmosphere and have some breathability under the dome. And so that was what they found most challenging, was how to create an environment that can sustain human life. While doing their research, though, they actually found that maybe Europa, one of Jupiter's moons, might be a better a solution for creating a community on and by the Red Planet. So that was Jupiter's Future Communities by Super Cool 2.
And then a young man named Raymond did a project on his own about Earth relocation. So this is the device that he built, and it has many features to it. So he was interested in what happens when the Earth is overpolluted and has no more natural resource. And so he built a space station and had the idea to load it up with a couple million people and go find another planet. So the space station uses rotational gravity. So clearly that was something the class talked about, rotational gravity. We're seeing that in several of the projects. It has a giant parachute and an inner core of bio-rocket fuel. And the little silver dots that you can see there on that model represent communities of people who farm and write and provide therapy to other people. And that was very insightful also, that they understood that therapy would be necessary for space travel. So.
And so the next project is by Ella, who wanted to do a comprehensive project on how you would live on different planets in the Milky Way. She concentrated on our solar system though, and she created a wonderful website and reported how life would look like on each planet. And she used clay modeling to bring the planets to life. So all of these pictures represent clay models of Venus, Jupiter, and the Earth respectively. And also she talked about the temperatures on each of these planets, and her website allows you to figure out where you'd be most comfortable. She also talks about the kind of food you might eat and how you might grow that food. And then she also includes really fun facts on her website, like it would take 12 years to get to Neptune, and Jupiter has 4 rings and 67 moons. So it's a very nicely done website. She also includes the sun, which she says you probably wouldn't want to live on anyway. So, but the website is very nice and comprehensive.
And Julian did this was a team, but there were several people on the team, but Julian was the leader of the team. And it was a project on building a space station, so astronauts would have a place to do research in space. So they talked about experiments that included analyzing samples, finding out how animals react to zero gravity, and testing robots. So, and Julian also designed this logo for the Python 1. So the space station has an advanced computer to operate critical systems. It has living quarters. It has, which includes recreation. It has an airlock for spacecrafts to dock, and so astronauts can go on spacewalks. And it also has an observation module with many windows.
All right, so our next project comes to us from Maya, and Maya is very fascinated by stars, and her project documentation included a very nice explanation about what are stars and how the sun is a star, but a really big one, and how stars are huge celestial bodies made mostly of hydrogen and helium. And she was really interested in getting astronauts to be able to see stars better. And so she developed something called the observation screen, which is so that astronauts can magnify the stars and see them from a safe distance. And then if the astronaut was interested in doing some research on meteors and space rocks, then she also built an observation tank that allowed you to it's a sealed observation tank, and the rocks are floating within the tank, and so they don't just float out into space. So you have a better idea of how to look at those rocks. And I think she has built a set of ladders so that you can step into the tank to observe the rocks. So this was Let's Look Closer, Let's Think Bigger by Maya.
And there was also a project by 2 team members called the Best Friend Duo. And they did a very nice project on how to build a robot to plant seeds on Mars. They thought that was a good idea to use robots because robots don't get hot or cold, so they could stay outside and be resistant to the temperatures on Mars. And the robots would also have a compartment to carry the seeds and the soils. And the surprising thing that they learned is that there are different kinds of robots, like rovers are considered robots. And they also made a very nice video that we'll be posting later on.
So the next project comes to us from Sam, and Sam built a robot called the Stargazer. And this robot goes into space and sends pictures back to Earth. But the main purpose of Stargazer is to identify small or unknown objects and send warnings about possible comets or asteroids that could be a danger to Earth. The problem it solves would be to warn scientists and people on Earth of dangerous asteroids. He's thought of a lot. There's a camera on the top of the robot. There's a vacuum inside to suck up the rock samples. Just like actually, I was just thinking about this project while listening to Dr. Wadhwa this morning, because that's exactly what some of her equipment looked like. And then, so he called this robot Stargazer, and some of the interesting facts that he found was it only takes 18 minutes for a photo to travel 209 million miles from outer space back to Earth. And his idea was to build flying robots that would orbit the Earth and Moon and Sun, where they can detect these asteroids and other flying objects near them and send that information back to NASA and Earth.
And then there was a young man named Deacon who actually built a model of a rocket ship that he proposed sending to Mars. And he talks about how the rocket ship has different compartments for different purposes. And this is a picture of his rocket ship, and his video we'll be posting later on.
Oh, no, sorry.
Oh, well, you can go ahead and show it now.
I
think we have
by
to.
mistake.
Okay, all right.
Sorry, that was my bad.
Okay.
Okay, so the next project comes to us from McKenna. Her project is called Like Space in Your Hands. McKenna did a very comprehensive project on a lot of different topics about how space affects humans. She wanted to know quite a bit about space in different ways. She learned interesting facts, like the fact that astronauts had to exercise 2 hours every day in space. She also learned that astronauts, because of their spines are compressed on Earth, so when they go into space and there's no gravity, their spines lengthen. So when they come back, they're a few inches taller when they come back from space. She was also, I think, a little bummed out to know that you weren't allowed to have any cookies or bread or soda on board the space station because of the crumbs that could actually get into different buttons and ruin some of the equipment. So this was Like Space in Your Hands by McKenna.
And then another young woman made a movie with Legos. She wrote the movie script and then made a Lego enactment of it. And the play was about how, well, it was a 2-act play, and part of the play is looking for the food and the other part is finding the food on the planet. So there were plants growing on the planet, and it was really a charming play, and we'll show you that when we post the videos.
And then finally, Claire made the air body cleaning system, ABCS. And one of the problems that she was trying to solve was the fact that astronauts couldn't shower in space because it's time consuming, and you can't have water, you can't shower normally with water, and it's also risky because of the potential for contamination with the water. So her solution was to have an air-based showering system, which used air pressure to blow dirt and dead skin cells loose, and then a vacuum to suck the particles. And then the station would be self-cleaning. It's designed to save space, and she designed it to replace the bathroom cubby that they currently use. So she discovered that the astronauts were sometimes not able to shower for 6 months or longer. And so she came up with the ABCS to help them stay clean. And the thing that surprised her was to learn that astronauts didn't shower quite so regularly in space.
And then the next group, well, it wasn't a group, it was a young man named Asher. And he was really interested in robots because he thinks robots are cool. And he hopes that in the future, there would be more robots, launching more robots would help us find future galaxies. So he also hopes that NASA will create air supply so that we can live on other planets. So, and he was surprised that the new rover was just launched.
So I want to bring in the engineering students now and talk a little bit about the NASA Micro-G Next. The NASA Micro-G Next Buoyancy Experiment Design Teams Challenge. It challenges undergraduate students to design, build, and test a tool or device that addresses an authentic current space exploration challenge. The overall experience includes hands-on engineering design, test operations, and public outreach. The photograph you see here is actually from NASA's website, and this was our students, I think in 2016 2017 or 2016. I'm not very sure, but once the first phase of the challenge is the design, and then 20 teams are selected, and GVSU has qualified in the top 20 for the last 5 years. The test operations are then conducted in simulated microgravity environment of NASA's Johnson Space Center Neutral Buoyancy Lab. We're going to show you a little video that the team made about the project, but then we have the team members with us. Like I said, one part of the overall experience includes public outreach. So this is very much part of their design challenge experience. So I'm going to start the video. It's a short 3-4 minute video, and then introduce you to the teams on the other side. Can you hear that?
No, there's no sound.
I'm so sorry. So hold on, I'm going to stop sharing. And then this is what I told myself, don't do this, share sound when you share. Okay, let's hope this works.
Stabilizing device to help take.
Okay, let's start again. Did you hear that?
Yes.
Hi, I'm Sienna Janicki, and I'm here with Grand Valley State University's team for NASA's Micro-G Next Challenge. The challenge's goal is to create a stabilizing device to help take rock samples on the moon. The main parts of this challenge are that it needs to be able to take a rock sample, and this is done by using a core drill and a diamond drill bit to be able to cut through any type of rock that's necessary. The stabilizing device itself needs to fit within a 6-inch by 6-inch cylinder due to the limited space capacity on the space shuttle. This challenge takes place at the Neutral Buoyancy Laboratory in Houston, Texas, to simulate conditions of a moon environment. It's very large, however, we won't be able to attend in person this year due to COVID. Here are some underwater pictures of the laboratory and some of the simulations that take place there. This is our team, the GVSU Moon Miners. The official challenge name is the Lunar Surface EVA Operations Lunar Sample Coring Device. We are one of 27 teams that made it to the competition stage from across the country. Our design includes a 3-legged stabilizing device with a spring compression. This helps indicate the 3-inch sample size that is required. We also have a handle that flips out to the side to help the astronauts get a firm grounding when drilling. And all of this is mostly concealed, so none of the rock dust can interfere with the moving components such as the springs. As you can see in the pictures, this is our design. You can see when the drill is attached to the stabilizing device and the handle is inward. You can also see when the handle is outward when the astronaut would be holding onto it. And finally, in the top right corner is when the stabilizing device is compressed. Our design was created with some major space obstacles for astronauts. That being that the spacesuit is very hard to maneuver and is very bulky. It has very large gloves and it is hard to grasp things. Also, it's very hard to force downwards, which is necessary for drilling, and is very hard to produce in minimal gravity or zero gravity. Also, as we stated before, the size constraints are very important because of the small space on the space shuttle. With these obstacles in mind, we created some solutions that could help. We created our design with a 3-legged device, or a 3-leg device with spiked bottom to minimize the movement and optimize the stability. We have an extra collapsible handle to provide astronauts with a leverage point to be able to force down when drilling. We also stuck to the very specific and strict size requirements and also could be collapsible. We're very excited to keep moving forward with our design, and if you would like some more information on some of the NASA activities, information, videos, or some of the other information that they have, we provided the link and we'd encourage you to check it out.
So this was the NASA Moon Miners. And that it brings us to the end of our outreach program. I do want to introduce the Moon Miners. They are Sienna Janicki, Jenna Stolzman, David Kowalskis, Danny Weller, Chad Brown, Paul Eggerding, and Connor Koss. And they are here with us, and they will be taking questions now. So I'm going to stop sharing and see if there are any questions. All right. Okay, can I have a copy of this video? Yeah, I think so. I think it's going to be on our Roger That video, YouTube video. So guys, I'll start then. Can you tell us about how you, what was the process about becoming one of these 27 teams at the end? Like how did that look? What was the process like?
Yeah, so we started, so the project is ran through the ASME Club, American Society of Mechanical Engineers. And I'm a member on the e-board of that society. And so we kind of put a team together, saw who was interested and reached out by creating a meeting. And that's how we kind of formed our team. And then after that, we decided on, there's different challenges that you can decide on to write a proposal for. So we decided on the Lunar Coring Device Challenge just because it seemed super interesting. And personally, I was a part of the team last year. And me and David Kowalskis were both part of the team that made it last year. And we kind of wanted to do something a little bit more complex than the device that we did last year. So we decided on the Lunar Coring Sample device because it seemed really fun. Yeah. And then after that, we, like I said, we had our team together and we just kind of brainstormed ideas, and there's a whole proposal writing process that you go through. And luckily, since we had just finished it last year, we had a lot of the same, we had a lot of good resources from our last year competition for the proposal. So we just went through our design process, which was very iterative and a lot of long nights of going back and forth on what we could do to stabilize the whole coring device, which is the main concern. How do you stabilize this thing while it's drilling? And how do you actually extract the sample from the coring device? So just a lot of brainstorming and a lot of fun collaboration with each other. And then finally writing the proposal. So delegating tasks to different team members and just, getting it done. And then obviously submitting our proposal and then waiting a month to find out if we made it.
Do you know how many teams there were in all?
I don't. I wish I did. I'm not sure though.
Yeah. Let's say 100. Let's just say 100.
Perfect.
So
No, go ahead, Karen.
Okay, could you talk a little bit more about why you chose 3 legs for stabilization and what the purpose of the springs are for those who may not understand all of that?
Yeah, for sure. So the purpose of the 3-legged design is to locate kind of where we want to drill where we want to drill it at and be able to kind of be more flexible. We noticed that last year they had the same design, and we got to actually watch virtually last year's coring challenge. And we noticed that a lot of the teams had just one leg with a core drill kind of going through the center. And it made it difficult to drill cores on surfaces that weren't exactly straight. So we noticed that and we took that into account. And that's how we decided on the 3-legged design, because it allows for taking a sample maybe that's on surfaces that are like this, because it can kind of move and
like an iPod too.
Yeah, so like it can move up and down. Yes, that's perfect, Connor. And then I forgot what your other question was. Sorry.
Oh, the springs.
Oh, the springs. Yeah, so the springs, we had to do some spring calculations to be able to decide on the exact spring that we would need for our system to be able to travel the 3 inches to collect the sample collection. So there's a lot of math that went behind that, and I won't get into all of that, but basically it gave us the force that we would need to actually push down on the device to drill the core sample. And that's really important because you don't want a spring that's too heavy for the astronaut to have to put his whole weight on to push down. So just a lot of calculations that went into that to select our springs.
All right, so we have an audience question from Debbie Morrow, who wants to know, amongst your team members, are any of them considering or hoping on becoming NASA employees in any capacity?
Actually, yeah. I mean, through this event, through this challenge, they give us a lot of opportunities for networking with NASA engineers and give us a lot of pathways for potential employment and internships. And I know that we do have a few members on the team that have looked into those opportunities and are pursuing them. They give us good like alumni panels to talk to, and that gives us good networking opportunities. So yeah, we definitely have some interest.
That's wonderful. So
Mhm.
is this going to be something that is for Artemis, the Artemis mission, or is this?
Yeah, actually, yeah, it's for the Artemis 2024 mission. Yep.
Okay, nice.
Mhm.
Yeah, I'm gonna see if we have any more questions. I don't see any more questions on the chat, but
Okay.
what were some of the things that you found surprising when you were designing this?
I mean, it's very different from last year, because last year it was, I'm sure not everyone knows, but last year it was an initial sample collection device. So we've essentially made like it looked like a little gun that basically just scooped up a sample. And so it's just like a trigger that you pull to collect the sample. It was very simple. There weren't too many components. And this year it was a very complex device, and we have a lot of components. And I think one of the things that I found very surprising was how different components actually work in space. Like for example, we have bearings that have to secure our drill, but also allow it to rotate. And for those of you who don't know, bearings are usually lubricated with grease on the inside to make sure that it runs efficiently. And one of the challenges in space is that they don't like to have bearings with fluid in them or grease in them, just because that can contaminate the other areas if it leaks. So that was one of a major design challenge that we had to go through, was how do we design something, or what kind of bearings do we pick them, because we're not familiar with other kinds. And so I just went into a lot of research and looking into different dry bearings, which were kind of interesting to look into. But yeah, just a lot of complex things in space that you normally wouldn't run into on Earth.
Right. I mean, and the 0G, or not Moon has a little bit of gravity, but still quite low, much lower. And so that's where the force, you were saying that
Yeah. So we had to take that into account as well when we were doing our spring calculations. We basically just had to, so the neutral buoyancy laboratory mimics 1/6 of gravity, of Earth's gravity. So we basically just had to divide our weight by 6, and that would be kind of mimicking that simulation. So
okay, nice. And then what things were very different in considering this challenge problem compared to ordinary engineering on Earth? It's related to your last answer.
Yeah, so it's very different. You have to take into account, like I said, the fact that you're not in a normal gravity condition. So the forces and the weights are very different. And then you also have to think about, how the astronaut is going to be able to handle the device, because obviously our hands are very easy to grasp things. But when you have a really big glove on, it makes it very difficult to grasp something as simple as just a little lever that you wouldn't even think. You would be like, oh, that's easy, and then we present it to NASA and they're like, no, that's a big no, like you cannot have that. So that was definitely a challenge, there's always a trade-off between making things too big, or making things big enough for the astronaut to handle, and almost too big so that you're out of your size constraints.
Well,
So that
brings
was.
me. So, did you have a consultant in NASA that you could run things by iteratively while you were doing this?
So for the proposal part, no. We're kind of on our own for that. Unfortunately, we are allowed to ask some questions, but for the most part, we kind of go through the design process on our own. And our faculty mentor, Dr. Manaharan, is really good resource for that, to kind of collaborate on questions. But now that we are past that, the initial proposal design, yeah, we have we have some engineers at NASA that we can talk to and collaborate with. So
Nice. And when do you go to present these? Or I know you can't go, but when do you send this to be tested?
so we send it in, I believe it's end of May. I know the test week is the second week of June.
Okay.
Yeah.
Okay. And do you have to provide some documentation or videos of how you want it to be used?
Yeah, so there's a lot more documentation that we will still have to go through. One of the next big ones is our TEDP, which is the Test Equipment Data Package. And that essentially gives NASA proof that we tested our device here at Grand Valley to make sure that it meets the requirements and everything. And then we'll also have a documentation of the operations plan. And that's a really big piece of paper to give to the diver and tells them how to actually work the device.
Nice.
So that's a really important piece of documentation that we'll have to go through.
Well, I see that our main speaker for tonight, Dr. Chow, has entered the room, and I don't want to put him on the spot, but sir, have you been in the neutral buoyancy lab and trained on it?
Oh, yes, many times. I've spent many hours, many hours training in the neutral buoyancy labs and helping to develop procedures for building the space station and testing equipment, things like that.
That's wonderful. So our students here have did the Micro Next Challenge, and they've proceeded to the next phase, and so they're going to build. Can you repeat that? The lunar drill? Is it a?
Yeah, it's a lunar sample collection device.
Oh, great. Super. Yeah. Excellent.
Yeah. So we just concluded the outreach portion of our Roger That. So if there aren't any more questions, I'm going to say thank you so much to everybody. And thank you to the team for coming and answering questions. And we will see you in a little bit with Dr. Chow.
Thank you.
And everybody, I'm going to have to close this one out in the recording, and then we'll start the new one. So I think Dr. Chow just missed my email before he came in, but we're glad.
Sorry. Yeah. So it's like, hello, welcome, goodbye. And then see you again.
Okay.
Back soon.
We'll open
Thank
it up
you,
really
Jenna.
fast.
Thanks, Connor. Thanks, everyone.